Hi, this is Mrs. LaBarbara. This is AP Physics, Chapter 13, Periodic Motion, Video 3. Today's topic is Simple Harmonic Motion, Part 2. The objectives are the same as last one, except we're going to talk more about equations and be able to do calculations with these equations. Displacement is sinusoidal function of time. So x equals a times cosine theta we learned in the last lesson. So if at t equals to 0, the phase or OQ makes an angle phi, then at a later time, t theta would becomes omega t plus phi. So x in general equals a times cosine omega t plus phi, where omega equals to square root of k over m. In this equation, x is the periodic function of time. So it could also be expressed as the sine function rather than cosine function using the identity cosine alpha equals to sine alpha plus pi over 2. In simple harmonic motion, the position is periodic, sinusoidal function of time. So what does that look like? It looks like a sine function. This is a special case though. This is one at t equals to 0, phi equals to 0. In this case, x will start at a and will vibrate between a and negative a. The period is time for one complete cycle. So omega, remember that's angular speed. Angular speed times time equals angular displacement. 2 pi, therefore t equals to 2 pi square root of m over k. How mk and t affect the period. So from this equation, t equals to 2 pi square root m over k, we know increasing m with the same a and k, it's kind of like you're stretching it out. So 3 has the biggest m. Increasing m, t increases. Everything else, the amplitude stays the same, but t increase. You can see omega decrease. Increasing k with same amplitude and same mass, you kind of squishing it. It's like you're squishing this. One has the biggest, smallest k, 3 has biggest k. You're pushing it toward x equals to 0, squishing it. So increasing k, t decreases. The time between the periods, the time between crest to crest becomes smaller. While you're increasing a, k and m remains the same, t doesn't change. You only changes the amplitude. Phase angle. So in this equation, x equals a cosine omega t plus phi, the constant phi is called phase angle. It tells us at what point in the cycle the motion was at t equals to 0. It's equivalent to where around the circle point Q was at t equals to 0. If we let x equals to x naught when t equals to 0, then x naught equals to a times cosine phi. So here are 3 phis. Phi equals to 0, this is when x equals to a, x starts with a. And this is phi equals to pi over 2, so that's where x will be less than a. And here, the special case in the gold color is phi equals to pi over 2, actual x equals to 0 at that time, at t equals to 0. So if phi equals to 0, x naught equals to a, so the body starts at its maximum positive displacement. If phi equals to pi, then x naught equals to negative a, that means the body starts at its maximum negative displacement. If phi equals to pi over 2, then x naught equals to 0. That means body is initially at the origin. So it's just moving back and forth. Right when it's at origin, that's when you start your timer. That's what it means. Velocity and acceleration as a function of time. So a equals a cosine omega t. Now v equals to dx over dt. So vx equals to the derivative of this function. A is constant, cosine. The derivative of cosine gives you a negative sign. Remember, this is a chain rule. So omega t plus phi gives you omega. So you have to times omega. That gives you negative a omega sine omega t plus phi. So the maximum x is the amplitude. The maximum v is a times omega. A equals to dvx over dt. So ax, again, is a times omega. Then the derivative of sine is cosine, and then you multiply another omega. So that gives you negative omega squared times a cosine omega t plus v. Remember, a cosine omega t plus v, that's x. So ax is negative omega squared times x equals negative k over m times x. The maximum acceleration is just a times omega. When x is a, right, that's a is max. So the maximum value is a omega squared. So as you can see, we have the same expression as before. We have derived this before from f equals to kx and ax equals to f over m. So from this x displacement, we derived the same thing. So this is a proof also x was correct. So that means the projection, we assume the projection is the simple harmonic motion actually is true, because the different ways have the same result. Let's take a look at displacement x as a function of time. Let's see how that how this displacement velocity acceleration graph relates. So if this is a displacement, then the velocity is this. Velocity vt is pi over 2 shift of x versus t graph. So you shift this graph to the left by a quarter cycle, you will become x. So here is the same one, you shift it to quarter cycle. So that becomes your velocity. You shift this to the left a quarter cycle more, that will become, starting from here, this will be your acceleration. Okay. So when x equals to x maximum equals to the positive amplitude, velocity equals to 0, acceleration is negative maximum. When x is at a maximum value, acceleration is positive max value, positive maximum value. Determine magnitude of amplitude, the amplitude, and phi, the phase angle, if we know the initial position and initial velocity. So we know initial position, when t equals to 0, x naught equals k, a times cosine phi, and v naught equals negative omega a sine phi, because we just substitute t equals to 0 in these two equations. We can use these two equations to find a and phi because you have two equations and two variables. First, we can find phi by dividing these two equations so we can get rid of a. Once we get rid of a, this becomes negative omega times tangent phi. Since we know omega, right, we know v naught x and x naught, we can find tangent. Tangent is just inverse tan. V negative v naught x divided by omega times x naught. Next, we can find a. We can find a cosine phi equals to x naught. That's what's given. From the second equation, we can find a times sine phi. That equals to v naught x divided by negative omega. So we can use a cosine phi squared plus a sine phi squared. We get, that gives us a squared, which equals x naught squared plus this negative squared. Negative squared is the same thing as positive squared. So a equals to square root of x naught squared plus v naught x squared divided by omega squared. So if we know the initial position and the initial velocity, we can find the phase angle and the amplitude by using these two equations. Let's take a look at this example. A spring is mounted horizontally. We know the K and we know the mass. From K and mass, we can find omega. What else do we know? We know the body's initial displacement and we know the initial velocity. We have to find the period, amplitude, and the phase angle. Well, period, remember using the equation, period equals 2 pi square root of m over k, plug everything in, m is 0.5, k is 200, we have 0.31 seconds. Omega, on the other hand, is square root of k over m, omega is 20 radians per second. The amplitude A equals to x naught squared plus v naught x squared divided by omega squared. Plug everything in, we have 0.025 meters. And the phase angle is inverse tan, which gives us a negative 0.93 radian. Okay, let's see why it's negative. We can also know because velocity is positive and x0, x naught is positive. That means if you imagine in the circle, it's moving in the positive direction, x is also positive, so it's in the fourth quadrant. So that's why phi is negative. Okay. Next one, write this equation for the displacement, velocity, and acceleration. Displacement is a cosine omega t plus phi. We substitute a, we substitute omega, we substitute phi. And v equals negative a omega sine omega t plus phi. Again, we substitute a times omega, which is 0.5, and sine omega t, v is negative. Similarly, we can find a equals to negative k over m times x. And so k over m times a gives you 10 cosine 20 t minus 0.93 radian. So in these equations, the phi is in radian. The displacement varies from negative 0.025 to positive 0.025, and velocity varies a times omega, which is negative 0.5 to positive 0.5. Acceleration is a omega squared, so positive negative a omega squared, negative 10 meters per second squared to positive 10 meters per second squared. So you can also check your result by setting t equals to 0. When t equals to 0, what is x, vx, and ax? Check your understanding. So a glider is attached to a spring. If the glider is moved to x equals 0.1 meters and released from rest, it will oscillate with amplitude a equals to 0.1 meters and phase angle equals to 0. Suppose instead at t equals to 0, the glider is at x equals to positive 0.1 and is moving to the right. In this situation, is the amplitude greater than, less than, or equals to 0.1? Well, amplitude equals x naught plus v naught x squared divided by omega squared. We know x naught is 0.1, v naught x is non-zero, so a has to be bigger. Next one is the phase angle greater than, less than, or equals to 0. We know if v is moving to the right, this is positive, x is also positive, omega is always positive, so this number is negative. That means really phi is negative. Another way to think about it is the glider is moving to the right, so it's in the fourth quadrant, so its x is also to the right. So the object must be in the glider must be in the fourth quadrant in a circle, so your phi has to be less than 0. Suppose instead at t equals to 0, glider is at x equals to 0.1 and is moving to the left. In this case, is amplitude greater than, less than, or equals to 0.1? It's still greater because v naught x squared is still bigger than 0. So a is bigger than 0.1. Is the phase angle greater than, less than, or equals to 0? Let's see. So v naught x is negative. So this value would become positive. So phi has to be greater than 0. Another way to think about it is the glider is moving to the left and x greater than 0. So that means the glider must be in the first quadrant in the circle, in the reference circle. So also from this point of view, phi is also greater than 0. That's it for today. Thanks for watching.